Hi everyone, I have bad news. As it turned out, almost nobody interested in watching detailed videos about Klipper firmware. Therefore, I had to slightly adjust my plans. In this video, I'll explain how to configure, compile and install MCU part of the Klipper firmware on the 3D printer board. Configuration setup I'll cover later in videos about my projects. I'll demonstrate the main configuration using my Duender printer as an example, and I'll show macros with my DIY AMS, which, by the way, after a vote on my Discord server, was decided to be called Medusa. In the previous part, we stopped at launching the Klipper host. The next step will be to compile and install the MCU part of the firmware that runs on the printer's board. The first thing you need to do is figure out which board your printer uses and how difficult it will be to flash the new firmware onto it. A quick warning: the actions described in this video could potentially turn your printer into a brick. Everything you do with your boards is at your own risk, and I'm not responsible for the result. I have 9 different 3D printer boards on hand, and all of them are now running Klipper. For this video, I literally flashed Klipper onto every board I could reach. All boards, both old and new, can be divided into two large groups: proprietary and universal. With universal boards, things are relatively simple, since they are designed to work in different printers, support multiple firmware builds, and come with the pinout documentations. Proprietary boards are more complex. In theory, Klipper can be installed on almost any board with the compatible microcontroller, but not all boards allow this without extra hardware and specialized firmware flashing skills. That's why it's often much easier and faster to buy a new affordable universal board. Personally, I prefer Bigtreetech boards. I've used them since 2019 and have never been disappointed. Also, boards can be 8-bit and 32-bit. The oldest are 8-bit boards, most of which use Atmega family microcontrollers. Klipper firmware isn't picky, and its MCU component can run on these old 8-bit boards. But there are no miracles. Outdated, slow microcontrollers simply can't deliver the same performance and feature set as modern ones. Even with those limitations, it's still a workable solution. To avoid jumping from topic to topic, we'll address each question in order. First, we need to understand the scope of the task. To do that, let's check if there is a ready-made Klipper config with instructions for your printer or board. Go to the Klipper page on GitHub and open the config folder. In the example list, you'll see configs with the suffix printer. If you find your model in that long list, congratulations, you most likely already have everything you need to run Klipper on your printer. You should also pay attention to the printer's release year, which is included in the file name, since manufacturers sometimes use slightly different boards in different production years. Ideally, check the version marking on your board, Google it, and confirm that the instruction applied to your exact board. If you use universal board, you won't find a fully finished config here. In the files labeled generic, you'll find partially prepared configs for specific boards. This includes all the main pins, but printer-specific settings such as print size or kinematic type will need to be configured manually for your own printer. But before all that, we first need to compile and flash firmware. To compile the firmware, connect to the host via SSH, run the command cd Klipper to enter the Klippers folder, and make menu config to launch the firmware parameter configuration utility. It's worth noting that the KIAUH utility offers the alternative method for compiling and flashing firmware. In the advanced section, you'll find the relevant options. Essentially, it's just a convenient interface that lets you run the necessary flashing steps without manually entering commands in the console. However, personally, no matter how hard I tried, I couldn't flash most of my boards with this utility. On the other hand, I received feedback from a subscriber who succeeded. We discovered that due to some changes in Debian, certain functions temporarily stopped working. Therefore, at this stage, the build-and-flash functionality in KIAUH is hard to call stable. So in this video, I will focus on old-fashioned flashing, since it's well documented, more or less universal, and it works. In the future, if the KIAUH option becomes reliably stable for all boards, I'll cover it in more detail. And so, let's return to menu config. If in the first step you managed to find your printer or board in the config list, then most likely it's enough to open the configuration file and look at the comments at the very top. They usually list all the main parameters you need to set in the configurator. Just follow those instructions carefully. But since I'm promised not only to copy and paste, but also to explain what, where and why, let's dive deeper in the meaning of these parameters. Enable extra low configuration options, turn this on, it reveals all settings. Next, microcontroller architecture. If you're not sure which microcontroller your board uses, you can usually tell by reading the marking on the largest chip on the board. Atmega AVR refers to all Atmel's 8-bit MCUs. Most 3D printer boards use two MCU types, the 2560 and the 1284P. Other variants do exist, but I haven't encountered any of them myself. Microcontrollers with the SAM architecture is also made by Atmel. You'll find them on Duet boards or their direct clones. For example, my Fysetc Big Dipper, a clone of the Duet.3 Mini 5 Plus, uses one of these MCUs. LPC chips come in only a couple of varieties and showed up on some boards 6 years ago. Lately, they are almost never used because most tasks can be handled by more popular STM32 series. Klipper supports a wide range of them. The STM32F103 is used as the main MCU on almost all budget boards, the F407 on high-performance boards and the F401 on mid-range boards. Other versions from this series do appear, but less frequently. Series like F0 and FG aren't used as the primary MCUs. Everything that follows is not needed right now. It covers microcontrollers for various peripheral devices and development debugging tools. For 8-bit boards, it's enough to select only the microcontroller family and model. All other parameters should set themselves automatically, and you don't need to change them. For 32-bit chips, there are more parameters and they differ. I'll use STM32F103 as an example since it has the most settings. The others are roughly the same. After choosing the processor model, you'll see the option called only 10 KB of RAM. Personally, I don't know of any boards that use an F103 with only 10 KB of RAM, so you most likely won't need this feature. This option was added only recently and was never needed before. The next parameter related to giga-device chips. A separate explanation is needed and I'll cover that at the end of the video. For now, we'll skip it. Then comes one of the most important parameters, the bootloader offset. What is bootloader and how it works? In the simple terms, the bootloader is the small piece of firmware written to the very first sectors of the microcontroller's flash memory. It's responsible to accepting and writing the new firmware to flash, setting up the necessary pins and interfaces for that task, or it gives control to the main firmware. The offset parameter specifies how much flash space the bootloader occupies so that the main firmware knows from which sector to start, and it protects the bootloader code from being overwritten during updates. If this parameter isn't documented, it can be hard to find. So using basic logic, if you don't know the bootloader offset, start with the largest value to ensure you don't override the bootloader and break your board. If the bootloader can't find the firmware, it means the offset is too large. Reduce it step by step until the firmware lands where the bootloader can find it. This is probably the riskiest setting, because choosing too small offset can damage the bootloader and prevent SD card flashing. In that case, you'll need a hardware programmer to recover it. The clock reference parameter is also quite interesting. In essence, it is a separate component on the board, a small crystal located next to the microcontroller and connected with two pins to it. When an electrical signal is applied, this crystal resonates, always at one precise frequency, usually 8 MHz or 16 MHz. The firmware uses this frequency to synchronize all of its operations. From this reference frequency, it calculates the MCU operating clock, all timers, delays, motor steps, and so on. Without the correct clock reference, the firmware will glitch or fail to start at all. However, this setting won't harm the bootloader, so you are unlikely to break your board. And finally, the last extremely important parameter is the communication interface. It controls how Klipper's MCU will communicate with the host. This parameter does not affect how you flash new firmware. It only controls which ports on the board's microcontroller will listen for commands from the host during printer operation. On most main control boards, you use one of the two options. The board USB port, which allows you to connect with the standard USB cable as the virtual COM port. On 8-bit boards, this is mapped as UART0. On 32-bit boards, it's usually labeled USB, but sometimes exposed like one of the MCU's UART ports. The second option is separate UART port without USB. In that case, the board needs exposed TX and RX pins so you can attach wires. On the host, those same pins must be available too. For example, on the Raspberry Pi's 40-pin GPIO header, pin 8 is TX and pin 10 is RX. Typically, the board's TX pin connects to the host's RX pin, the board's RX pin to the host's TX pin, and their grounds should be connected too. I don't use this method myself, so I'm not familiar with the problems it might have. Most ready-made configs include both connection options. Like the clock reference, this parameter isn't critical for the board. If you get it wrong, the host simply won't connect to the MCU, but you can always refresh and try again. For some microcontrollers, you can also see CAN interface, in addition to USB and UART. CAN is often used to link expansion modules, extruder ports, smart sensors, and so on. And on all-in-one boards such as Bigtreetech Manta, where the host and MCU share a single board, CAN replaces the USB cable. I haven't worked much with CAN. It's a large and complex topic. In the future, when I have enough hardware and experience, I'll cover it in more detail. USB IDs, it works fine by default. This setting defines which vendor ID and product ID the board presents when connected, so the operating system loads the correct driver. The option to use the chip ID serial number lets you pull a unique ID from the MCU itself, making it easy to connect multiple identical devices to one host. The optimized stepper code for step-on-both-edge parameter, to be honest, I don't fully understand it. It appears to move part of the stepper pulse generation to a hardware timer on the MCU, which should slightly accelerate step pulse processing and reduce CPU load. It's enabled by default, usually causes no issues, and can be left on. And in the last item, you can configure a forced pin state that will be applied before the firmware starts. To explain, I have an example. On the Bigtreetech Ep.3 Mini 1.2 board, the config tells you to enter exclamation point, which means inversion, with the pin PC13. If you look at what that pin controls in the configuration, you'll see it manages the USB pull-up resistor. It should be inverted at startup, which in this case means active. Otherwise, the USB device may glitch or not work at all. You rarely need to change the settings, config files usually note it. That's basically all the important settings in menu config. You can press escape, agree to save the parameters, then run make, and wait for the firmware to build. Now comes the most confusing and unclear step of installing Klipper on the MCU. As you already know, the bootloader is responsible for writing firmware. It controls how you can install new firmware onto the microcontroller. On 8-bit Atmega boards, bootloader almost always supports flashing a hex file over USB via virtual COM port, using the board USB to UART chip, typically a CH340, FTDI, or Atmega 8U2. To flash, connect the board to the host with a high-quality USB data cable. Before flashing, stop the Klipper service with the sudo service Klipper stop. Then run the flash command. Klipper includes a special utility make flash. It takes the settings from the menu config and based on them launches one of the built-in flashing utilities with the correct parameters, DFU util, BOZAC, and so on. For 8-bit boards, the utility is AVRDUTE. You can also use all these tools manually. Many boards include the exact command and parameters in their config examples or instructions. The makeFlash method is described in the official instructions and works for boards based on the Atmega 2560. First, find the device ID by running ls dev serial by ID. Or in the latest Klipper versions, open the web interface and under the Machine tab, click the Device button in the System Load section on the top right. That shows all addresses assigned to USB devices. Copy the path by ID. Then in the terminal run make flash device equal and paste the copied ID. The firmware will be flashed. If both make flash and direct AVRDUTE command fail to write the firmware, even though the board appears connected, It may simply have no bootloader. This is a known issue on old 8-bit Creality Ep.3 V1 boards. You can find many online tutorials on how to install a bootloader. Here is how I usually did it with Arduino Uno. Download an old Arduino IDE version 1.6.9, add and install the Sanguino bootloader, connect Arduino Uno and flash it with the Arduino ISP sketch from the examples. Standalone ISP programmers often run into firmware mismatch issues or other problems, so I stopped using them. Unplug the Arduino from USB, connect it to the board's ISP port using the diagram you see on the screen, then reconnect the Arduino to the computer USB. The printer board must be disconnected from power or USB at this point, only the ISP wires. In the Arduino IDE, I select the Sanguino board, processor 1284P, 16 MHz, leave the serial port set to Arduino's Uno port, choose Arduino as ISPs programmer, and click Burn Bootloader. After that, the board can be flashed normally over USB. Config examples usually show a direct AVR-dude command with parameters, but with my Ender-3 boards, the AVR-dude command from instructions rarely worked. Instead, make flash device with the direct path, for example dev-tty USB 0, usually worked. After flashing, restart the Klipper service or simply reboot the system, which is even more reliable. Besides the Ender board, I also have an 8-bit Creality 2.4 board from the CR10 Max or something similar. This board is terrible. All the extruder and X-axis related pins are routed to the ribbon cable with no labels, making it very inconvenient to use. But surprisingly, it's even had a bootloader, and Klipper installed on it just fine using the official Ep.3 instruction. And I also have a strange old proprietary board from MBOT mini printer. There is absolutely no information about it, and it had no bootloader. But on it I found ICSP pins. I couldn't find a wiring diagram specifically for this board, so I connected using the standard ICSP pinout, using the marker dot on the board, which usually marks pin number 1 on the connector. I wired everything according to the pin names and burned a bootloader. In this case, not Sanguino, but a standard bootloader for the Atmega 2560. And that's it. After that, Klipper installed normally using the standard instructions. For 32-bit boards, the variety of microcontrollers and bootloaders is much greater. There are 3 main flashing methods. One is using a file on the SD card, another is using a USB cable with the make flash command. The last resort is using a programmer like ST-Link to write firmware directly to the microcontroller by passing bootloaders, usually via the SWD port. This method is the last chance to flash or revive a board after a failed upgrade. It has many nuances and I am not fully familiar with them myself. Therefore, in this video I will not covering flashing with the programmers. Maybe next time. Most budget 32-bit boards support installing firmware from an SD card. It's worth noting that there is the way to flash these boards over a USB cable. Klipper includes a flash SD card script for this. It's supposed to mount the printer's SD card, write the firmware file to it, and initiate a reboot of the board. However, in my experience, that script have never worked. So we'll stick to the classic method until flash SD card becomes reliably stable. In any case, the first step is to download the compiled firmware from the host. Usually you use an FTP program for this. I use FileZilla. You need to go to the Klipper out folder, download the Klipper bin file and rename it to the firmware bin or wherever file the board requires. Or there is a simpler way. Enter the command that you see on the screen to copy the firmware file into the config folder visible in the web interface. With this command you can also rename the file to the required format. After that, in main sale, you'll see the firmware file ready for download. Most of the time it's enough to copy firmware bin onto an SD card, insert it into the printer and power it on. The bootloader should pick up the firmware, install it and rename the file name to firmware car. At this stage, a common problem is that the printer doesn't see the file on the SD card. First, make sure the firmware file has the correct name and is in the right place on the card. If you don't have exact information, try different names. A second cause can be the SD card itself. Generally, suitable SD cards for flashing boards are 4 to 8 GB or even smaller. Cards that come with the printers usually work, but they are very low quality and sometimes fail over time. In that case, you need to find a small but high quality card. The card should have only one partition and one volume formatted as FAT32. I've personally had situations when the printer didn't see even a proper card with the correct file system and file name. In that case, simply trying different SD card eventually finds one that works. But the most important advice I can give you when flashing boards via SD card is this. If something doesn't flash on the first few tries, don't rush and don't immediately grab the hardware programmer to try and install everything manually. A programmer is the absolute last low-level solution. Without understanding the process and having the necessary skills, you can very easily turn your board into a complete brick, or at least break the bootloader and lose the ability to flash via SD card. So before programmer, make sure you tried every possible option. Very often it helps to return to a stable reference point. Try to download and install the original firmware from the manufacturer. Obviously, the board firmware must be installed and updated somehow. And if you find the way to install the original firmware, then under the same conditions you can install Klipper as well. By the way, if after Marlin you install Klipper and your printer's screen shows nothing but a backlight, don't be alarmed. The interface needs configuration files on the host, and until you connect the MCU to the host and configure the display, the screen will simply light up. I have 6 32-bit boards. 4 of them can be flashed in this way. Just put firmware bin in the root folder on the SD card. It's worth noting that all these boards are from Bigtreetech, which always try to make boards easy to flash. Therefore, almost all Bigtreetech boards support this method. The same approach is used for most mellow boards, some Fysetc boards and others. MakerBase, for example, usually needs a different file name, but the principle remains the same. In theory, 32-bit Creality boards should also be flashed this way. They typically use standard STM microcontrollers. F103 boards expect a firmware bin in the root folder. F401 boards expect firmware bin inside a folder named STM32F4_update. You may also come across method where the bin file name doesn't matter, but it must be different from the name of the firmware that was installed previously. For most Creality boards you can find working instructions in the Klipper examples or in the user's manuals. But there is another unpleasant issue you may have. Your board might not use an STM32, but strange GD32. Where did they even come from on stock boards? In early 2020, COVID-related chip shortages made STM32F103 hard to find, so many printers temporarily shipped with the GD32 clones from Chinese company Giga Devices. By the middle of 2023, STM32 supplies recovered and the GD boards just disappeared. If you find board with the GD32 instead of STM32, not only on Creality boards, don't be surprised. It's simply a result of that temporary crisis. I don't have a single board with that microcontroller, that's why I turned to my Discord server for help. By the way, you are welcome to join. There are many interesting and smart people ready to offer advice. I also post beta versions of my projects in that server, and people share their own modifications and upgrades. Together with a subscriber named Roxette Boxer, we pulled our efforts to revive his old GD32 based boards, and we succeeded. Many thanks to him for double-checking everything and describing the entire procedure in detail. To avoid making this video too long, if you need more information about GD32, you can join the Discord server and read the pinned message in the 3D Help channel. Personally, I've only come across that microcontroller once, long ago on the Voxlab Aquila printer. Back then, only 128 MB SD card worked. Yes, megabytes. The bin file name wasn't important and it had to differ from the previous firmware's name. And the file needed to be placed not in the root directory but inside a folder named firmware. I've never seen that method again, but it's possible. Boards that should be flashed via USB must first be put into a special flashing mode. In practice, there can be several different modes, each using its own flashing utility. One very common mode is DFU, Digital Firmware Update. To enter DFU, the board typically has pins labeled boot 0. You place a jumper to short them, and on power up, the board enters DFU mode. This is the built-in STM32 feature that lets you rewrite the entire MCU memory even without the bootloader. If a board only supports this method, Klipper can be built without a bootloader offset. Flashing can be done with the command make flash using the address shown by ls USB command for DFU device. Make flash runs the DFU util and writes the firmware to the MCU. I don't have an example of such a board right now, but not long ago I flashed a Fysetc Cheetah 3.0 board, which uses exactly this method. It's an interesting case. The board came out over 2 years ago, and Klipper installs on it just fine following the instructions on Fysetc website. Yet it still hasn't appeared in Klipper's own config examples, even though earlier versions of that board are there. My point is, don't limit your search for instructions and parameters to Klipper's examples. Often working instructions, especially for rare boards, come only from the manufacturers themselves. The second method I've come across is the Sum Boot Assistant, used on Atmel microcontrollers. I used this mode for Fysetc Big Dipper. Another interesting example. As I mentioned, it's almost a complete clone of the Ep.3 Mini 5 Plus. To install reprap firmware on it, you can use the original Duet instructions and firmware. However, the manufacturer provides no information on Klipper compatibility. But since the original reprap instructions works, the Klipper instructions might work too. In Klipper's config examples, I found the Ep.3 Mini board, entered the suggested parameters in menu config, of course after making sure the board has the correct microcontroller, and discovered how to enter flashing mode. With the board powered on, press reset button on the board twice. Then make flash device dev tty acm0, successfully installed Klipper. There are a few other methods that Klipper knows for flashing boards. Unfortunately, I haven't used them myself and can't describe them in detail, such as using the STM32 flash utility over UART or the CanBoot option. You may have heard about Catapult project, a configurable custom bootloader for control boards and additional devices. Originally, it was the CanBoot project, which was created to improve Klipper's interacting with the external devices, like extruder boards. Later it was renamed Catapult and gained support for full-featured MCU. This bootloader can be installed on many boards and lets you forget about SD cards, special modes, and so on. You can flash boards by running prepared script that automatically put the board into the needed flashing mode. I won't focus on Catapult in this video since I'm not very familiar with it yet, but I will explore it in the future and report back. The last interesting example I encountered while flashing everything at home is the Lerdge K board. It's not typical board, it's universal, but its firmware is closed source. I won't discuss the original firmware now, it's decent and user-friendly, but not very flexible and lack many modern features. At one point, Lerdge officially released instructions for installing Klipper on their boards. There were two important points. It seems menu config didn't know how to build the firmware in the required format by default. So Lerdge suggested modifying the file responsible for creating the firmware before building. After that, you have to pass the compiled firmware through the special utility that encrypted the binary so the board would accept it. In theory, then you can copy the firmware onto an SD card, go into the update menu of the original firmware and launch the update with the new file. In practice, I was never able to build firmware with the correct menu config parameters and the modified build file. No matter how hard I tried, I couldn't find a solution. In the end, as a last resort, I tried taking a ready-made firmware binary from the instructions, and it installed and worked. Of course, that's a cheat and doesn't fully solve the problem. The issue with using someone else's binaries is that sooner or later the firmware on the board will become outdated. When its version drifts too far from Klipper version on the host, the board simply won't be able to communicate anymore. Besides that, setting up the original screen from Lerdge is almost an impossible quest. So yes, I was able to get Klipper running on the Lerdge board, but I can't call it a complete solution. The very last step to make sure Klipper is correctly installed and configured is to connect the host to the MCU. This video is already long, so I'll skip the details. Klipper needs a minimal set of configuration files to run. Usually they are created automatically during installation. If the main file, printer CFG, is missing, you must create it manually. It should contain the basic sections for each printer component, a printer section with the kinematics and speed limits, settings for each axis, for extruder, bed, fans, and so on. Some settings are required for Klipper to start, others can be customized as needed. If there is already a ready-made config for your printer or board, just copy it into printer CFG and you'll have almost everything set up. If there is no config, you'll have to configure everything manually, but that's a big topic for a future video. Right now we only care about one section in printer CFG, the MCU block. It has a serial parameter where you must specify the address assigned to the board. You can find it by running ls-dev serial by ID or by path, or by looking under devices in main cell. Usually Klipper doesn't care which of the listed addresses you use, just pick one. If you plan to connect multiple identical boards to one host, make sure each path is different. After you set the parameters, save the file and reboot. If your board is already connected in the printer and you used a ready-made config, you should see your MCU listed under Machine System Loads alongside the host. If your board has a ready-made config but it's only connected to the host, you'll see an error about temperature being too low. You can temporarily set the minimum extruder and bed temperatures to -273 degrees just to confirm the board has connected. If no configs exists, you'll have to wait for the next video, where I'll explain how to configure all the printer's main components using my homemade duender as an example. Despite that mountain of information, there are many more possible situations and methods you might encounter. I tried to cover the most common cases. The variety of boards and microcontrollers is huge, and every manufacturer thinks it's necessary to add its own features, which only makes the life harder for users. But we work with what we have. As always, thanks to everyone who watched until the end. I'd be very grateful if you support the channel financially. All the links are in the video description. Like, comment, subscribe. I hope the video was useful. And that's all for today. See you soon.